Hello and welcome to this presentation on ANSYS Workbench Mechanical. We're going to look at mapping stresses into a model using the external data object on the project page. Here's the project page for this demonstration. I have a structural model on the left. I'm going to reuse the same engineering data and geometry in a model on the right. When I ran the model on the left, I exported some of the stress results into external text files. Then I used an external data system to read in that stress data, and I mapped it into the setup for this downstream model. In that way, I brought stresses calculated in one analysis into another analysis as initial conditions. I'm going to review now some of the detailed settings involved. Here's a simple model. We've placed a fixed support on one face here and a pressure on an edge out there. The model deforms in the manner that you might expect, and we can see how it deforms if we do a short animation. This example has been meshed with high-order tetrahedrons. It's a simple linear model. We look at the state of the stresses. There's a plot of the stress state. We can set up plots of the normal stresses. These are in the global coordinate system in X, Y, Z, and the shears in XY, YZ, and XZ. We can also put in a plot of vector principal stresses. Now there's something interesting that you can do when you want to export these. If I do a right click on any of these results, I can export them to an external text file in a format that's compatible with a spreadsheet. If I go up to Tools and Options and go to Export, note right here that when I export these things, I can choose to export node numbers, yes or no, node locations, yes or no, and here it says show tensor components. When I put in vector principal stresses and export, if I choose yes for tensor components, what I'll actually get out is sigma x, y, and z, and the shears xy, yz, and xz. Whereas if I was to use no for tensor components on this vector principal stress, then I would see sigma 1, 2, 3, and I'd have 3 orientation angles output. If I'm trying to map stresses into another model, I would typically want to use the yes selection so that what I really export are the sigmas x, y, and z, and those 3 shears. Let's review the export. If I click on an object and right-click and go to Export, Export Text File, I've already set up my export so that it will put out node locations, and here I will put out a column of stresses to go along with them. Let's just put in a file name test. On this computer, Excel opens up, and you can see location X, Y, and Z, and beside that, a column of the normal stresses, and they will be in the X direction that I specified. I can do the same thing for those in Y, Z, and the 3 stresses. Alternatively, if I do it for vector principal stress, I'll get all 6 stress components in addition to the locations of nodes. I can either use these 6 outputs to do a mapping to another model, or I could turn to the one file written for vector principal stress in order to do the mapping. Let's go look at the setup for external data. So we right-click and edit, and we open up this alternative view back on the project page. What I've done here is read in 6 files, one for stress in X, Y, Z, and one for each of the 3 shears. Let's go look at the first one. I read this file in. It's the one with stresses in X, written out from the object in the first mechanical system. Down below I tell it to skip the first line, that's what contains the titles, so I start at line 2. I know that the content of the file uses delimited, and I know that it has tabs to separate the different columns, so I put those in. I have to be very careful that I indicate the units that I'm in, and it happened to be millimeters. I also used the original global Cartesian system when I exported the data. I know that I have not had any transformation in X, Y, or Z, so I just leave this at zeros. Columns in the file that I've read in have different kinds of data. The first column contained X coordinates because I did not write out the node numbers. The second, I tell it it was Y. The third, I tell it it was Z coordinates. And the fourth column I know was stresses. Here again I have to indicate what the units were. That's consistent with millimeters. And I write in my own identifier. I know that it's sigma x, so I'm putting in SX to make it easy for me to remember later on. Down below I get a preview of the first several lines of the file. I know I'm skipping line 1. That's why I put a 2 over here on the left, start import at line 2, and there I'm picking up X, Y, Z coordinates followed by stresses, and I know from the name of the file that this was my stress in the X direction. I've done the same things for Y, Z, and for 3 shears. And if I look at a shear, I've indicated the first one's the master file, so I do not have to repeat the meaning of these columns. I know it's all the same nodes, and they all have the same coordinates, so I simplified it a little. I'm telling it that I am again using delimited data, and tabs are used for it. The rest is redundant because I've made the first file the master. I'm not using these columns, but I know that the one that I do employ is the stress column. Again, megapascals. I type in my own identifier for later use, and I can see the numbers being used down here. Time to move on. I close this. Now let's have a look at the system that has the stresses mapped in. Here are the loads, and all I have is the same fixed support. I do not have a pressure on the face on the edge of this object. So there's the fixed support. I have, back on the project page, an imported load. We'll see here that what was imported was an initial stress. Here's the state of stresses, and it will look the same as the state of stresses in the source model. What we've chosen to plot here to preview it is the equivalent von Mises stress, and it will compare to what you saw earlier. As for the transfer summary, you can see here that we did not miss any nodes, so that at least is a good sign. When I look at the imported initial stress, at first I can't see this plot. I have to go along here and choose what each of the column inputs will be. You can see stress X, Y, Z, XY, YZ, and XZ, the 3 shears. Let's review the settings for the mapping. There's the body to which we've mapped. We've mapped to corner nodes. We've chosen to do it so that we get continuously changing stresses, whereas if we mapped to elements, there'd be one value per element. Let's re-import that load, and you'll see here the state of von Mises equivalent stresses, which is what we've chosen to review. We've been in the global coordinate system, so there's no transformation in space. There's the equivalent stress that we're using to compare to the original. We could have brought in others, but we've chosen this one. There's the mesh. It's a different kind of mesh than we had before. This one is of hex elements. Again, we can review what we did, what we brought in. Looking down in the details, you'll see that we didn't show the points. These are the points from which stresses were mapped. You can compare them if it helps you check that the geometry was aligned properly. We've chosen manual settings, although the entries that we've used below, triangulation and volumetric, are what you'd get on defaults. You could go for distance-based average or for kringing as a means of mapping. We used other default settings down here in the named selection creation, and in advanced it was just the defaults for a mapping. We'll need to solve this model again. Now we can look at a stress result. There's the deflection. It's similar but opposite in direction to that of the original model, because in this model there's no load applied, just the imported state of initial stresses. So when those stresses try to relieve themselves, you'll get a movement in the opposite direction. We can animate it and check how the thing moves. And if we were to go look at the state of stresses, they're a lot closer to zero. They're not right at zero, but whereas they were up around 10 megapascals before, now they're down around 1.29 because we don't have any loads applied. Just that state of initial stresses. There's no load on the edge there, so you're not going to get exactly a zero state of stresses, but it does relieve itself quite a bit when it's unloaded, and the residual stresses produce the movement you see. There's the final deformed shape again. And that's a quick review then of the various settings required to map a state of stresses from one model to another. Reminder here that you have to ensure that these column settings are set properly. Thank you for joining me.